welcome to the course Advanced Reaction Engineering. Today already we have started discussion on the non-isothermal reactor design. So, today we will discuss about the ignition extinction curves for the non-isothermal reactor design. So, in this case ignitions and extinctions curves are how to draw, and so what are the different steady states are there. So, that we will basically discuss. So, in our previous class we already have discussed that means from the energy balance equations how to develop the energy balance equations, and from the energy balance equations heat generations and heat removal terms, that already we have discussed. So, here this is the general equations we have discussed in our previous class. So, if we split up these equations, this part as a heat generations that we have right here in the left hand side components, and the right hand side component, that part is the heat removal term. So, this is this. So, here two components or two way we can write, and these conversions also we can write tau k by 1 plus tau k, then heat generation terms for a particular reactions when that reactions we operate in a reactors. So, then heat generation terms we can write this way, or also if we know the Arrhenius equations. So, then reactions rate constants we can split up this way, pre-exponential factors exponential minus E by RT. So, means activation energy and temperatures we can write, and we can express the heat generations this way for this for any reactions, and this is the heat removal term. So, here this kappa we can express this way, and Tc that we can write this way, that already have discussed. Here T is the ambient coolant temperature, T0 is the inlet feed temperature, the temperature at which we feeding the feed or reactant component in the from the inlet of the reactors for the reactions. If we assume that reactions will take place at temperature T, so then accordingly if let us say the reaction is exothermic, then heat generation should be there. So, once the heat generation, once the progress of conversions is there inside of the reactors, so gradually heat generation should be there. So, heat exchanger, since we have designed a reactor CSTR reactor, so with heat removal or coolant that would be passed outside of the reactor. So, therefore, heat removal from the heat generated inside of the reactor. So, how means this way we can see heat removal terms or heat removal from the reactors we can specify or we can calculate. So, from these equations also we have discussed that. So, at particular temperature, so when the reaction temperature will change, so then RT and GT, that is heat at this particular temperature, so what would be heat removal at this particular temperature, what would be the heat removal at this particular temperature, what would be the heat removal. Similarly, at this particular temperature heat generations, if we change or want to do the calculations, so then these tables will get, and from the tables if we plot RT against T, so then these straight lines will come. So, that is heat removal lines, and similarly if we plot in the same graph GT against T, that is the temperature. So, then heat generations curves would be like this. So, here both the curves means heat generations and removal lines looks like this in general. So, for a particular example, so here both the line intersect at this particular point, so this point and this point. So, here heat removal and heat generations would be the same, means the reactors will operate at steady state, means these two top point is steady state 1 temperature, this is steady state temperature 2. So, these are the temperature where we can operate the reactor. So, now ignition extinction curves will develops, means at this particular profile or this graph. So, here this is the TA or you can TC, or the temperature T0 also you can say T0, that is the temperature at which the feed is entering. So, once it is the reactions which progress inside of the reactor, these are the two temperatures, that possibility is there. So, means these are the steady state temperature we can operate the reactor. So, now one by one we will discuss and develop some ignition extinction curves for this particular for any reactions, and after that we will take one examples that we will discuss. So, here you can see, let us say T01 or TC1, that is the inlet temperature of the feed, that at the beginning we have started with very low temperatures for that reactant mixture, that is we are feeding in the reactor, that at T01. So, this particular red dot you can say this is the T01 or TC1. Okay, so, this particular point you can say. So, once that particular temperature we are feeding the feed in the reactor, so then the heat removal curves would be A line, and heat generation lines for this particular reactions would be this. This is RT and this is GT. So, here one intersections is there. So, one point is there. If we start the reaction, means if we pass the reactant or feed through the inlet of the reactor, one point, this the blue point, that is the TS1. TS1, that is the intersection point, means heat removal and heat generation curves intersect at point 1 when T01 is the feed inlet temperature. Similarly, if we pass the reactants at temperature T02 or TC2, so that is the red dot. So, means x axis, that is the temperature from left hand side is the low temperature, right hand side if we move, that is the gradually high temperature. So, if we feed the reactant at this particular temperature, so then this RT curves would be B curves instead of A curve. So, now when TC2 or T02 is the feed inlet temperature, then the lines would be like this B curve, and at this particular temperature, so heat generation, that is due to the reactions, that would be same. So, here you can see two different intersections points are there, means two steady state temperature are there, TS2 and TS3. This is the TS3 and this is the TS2. So, these are the steady state temperatures. Similarly, if we increase the feed inlet temperature gradually, so then like A, B we already have discussed. Similarly, C means heat removal lines, RT lines, means if we change T01, T02, T03 like that way, T06, this is the T06 means feed inlet temperature. So, by that way if we look into that, so here, so when line A was there, means heat removal lines with the heat generation curves, that is crossing point at point 1, line B that is crossing at point 2 and point 3. Similarly, line C, that is the heat removal lines, that is crossing 4, 5 and 6. Similarly, line D, that is also crossing 7, 8 and 9. Line E, that is crossing point 10 and point 11. So, two steady state points we can, means if feed inlet temperatures, that is T05 or TC5 is there. So, at that particular temperature, that steady state point we can get point 10 and point 11. Similarly, if we further increase the feed inlet temperature T06, so then only one steady state, that is TS12 we can get. TS12, this point is TS12 for when feed temperature is T06, we are feeding the reactant. So, this way means we can see from left hand side to the right hand side, if we change the feed inlet temperature, what would be the effect, means how many what are the different steady state temperatures will be there inside of the reactors when the reactions we are conducting inside of the reactor. So, that is called multiple steady state possibilities is there depending upon the feed inlet temperature. So, if we summarize these observations, means these curves if we summarize, so you can see that when feed is entering at temperature T01, so then only one steady state temperature, that is TS1, the temperature inside of the reactors we can get, means here this is the T01 feed inlet temperature. If T01 is there, then one steady state temperature we can see for that particular reactions. Okay. So, when T02 is the feed inlet temperature T02, so then there TS2 and TS3, two different steady state temperature might possibility is there. If T0, similarly T03, there is also three different steady state temperature is there, T04, TS7, TS8, TS9 steady state, three different steady state temperature possibilities are there. When T05, TS10 and TS11, these are the steady state reactor temperature possibilities there, and T06, then TS12, that is the reactor temperature or steady state temperature. Under that we can operate the reactors. Okay. So, now if we plot here, we have got in the T0 means feed entering temperature, and this is the reactor temperature or steady state temperature. So, now steady state temperature in the y axis, these are the temperature, steady state temperature. If we this temperature, if we plot in the y axis, and feed entering temperature we put in the x axis. Okay. So, once this is the when T01, that is the feed inlet temperature, red one, red dot, that you can say it is the feed inlet temperatures, and corresponding steady state temperature is 1. Similarly, if we go T02, then corresponding steady state temperature is this, T03 steady state temperature 4, 5, 6, and T04, that is the feed inlet temperatures. So, then steady state temperature is 7, 8 and 9. Similarly, this way we can T05 and T06, if we go this way we can get the different steady state temperature. Now, if we join point 1, 2, 4, 7 and 10, so the lines we can get, this is called lower steady state, these are the lower steady state line. And see, similarly, if we join 3, 6, 9, 11 and 12 points, this is called upper steady state line, okay, or upper steady state. For this particular observations, for this particular systems or operations or reactions, if we conduct inside of the reactors, heat removal and heat generation both are there, and depending upon the feed inlet temperature, these are the temperature, steady state temperature we can get. Okay. So, now entering temperature, steady state temperatures, let us say, means if we go, it has been observed that if we means feed inlet temperature, once the reaction has started, feed inlet temperature if we started from here and gradually increase. So, it has been observed that from 10 to 11 it is sudden jump should be there, and then it reach to here. Okay. Means after 10 we should expect it would reach like this, but it is not happen. So, it is jump, sudden jump of the temperatures, you can see steady state temperature jump is there, means 10 to 11 should be there, and after that it would go like this. Okay. So, then point 11 is called ignition temperature, sudden jump of the temperature inside of the reactor is called ignition temperature, sudden jump. Okay. This temperature is called ignition temperature, temperature 11, TS11, you can see it is a ignition temperatures. So, similarly, it means here we have started the reaction, means feed temperature here, and steady state temperature was there, and gradually if we increase the feed inlet temperature would be like this way, it is jumping here. And now, if we start the reactions at high temperatures, reactor operating at TS12, in the this is the case 1. So, and this is the case 2. So, if we operate the reactors or started at TS12 or T06, that is the feed inlet temperature, means steady state is TS12. At that temperature if we start the reactions and gradually decrease the temperature. So, we are decreasing the temperature like this way. Okay. So, if we decrease the temperatures this way, means feed inlet temperature, so then the overall reaction temperature or steady state temperature will drop like this way, and once it is reached to the location 3, from here if we go this way, so it is decrease, and after that sudden drop would be there. Okay. So, from 3 to 2 means sudden drop of temperatures, here also sudden jump of the temperature it was here observed, and so when we are decreasing the temperatures, the steady state means feed inlet temperature we are decreasing, and means we have started at the beginning high temperature at 12 here TS12, and then if you decrease the temperatures it would reach here, and then sudden drop of the temperature we can observe, and then it reach to here. So, this temperature is called extinction temperature. Okay. So, this temperature is called extinction temperature 2, that is the TS2, that is called extinction temperature, and this is the ignition temperature. So, and this curve is called extinction curves. Okay. So, how to obtain this ignition and extinction curves for a reactors when we are operating at different feed inlet temperatures. So, then this kind of observations of curves we can observe. Okay. So, now and here's other point is 5, 8, that is in between 3 and 10 points. So, these are called unstable or unstable steady state temperature, unstable temperature. So, at this particular temperature we not operate the reactors. Okay. So, now stability of multiple steady state temperature we will discuss. Okay. So, means how to obtain ignition extinction curves that we have discussed. So, now stability on multiple steady state temperatures. Okay. So, depending upon the feed inlet temperature, multiple steady state possibility is there, means multiple steady state temperature we can observe when a reactions we are conducting inside of the reactors, their heat removal or coolant that is passing outside the reactors, means heat removal means heat generations. With the heat generations, since if there is reactions and the reaction is exothermic, then heat generation should be there, means heat formation should be there, and for that if we conduct the reactions at steady state operations if you want, then heat removal through that coolants or coolant circulation should be there, that is heat removal. So, depending upon that heat removal and heat generations curves or lines, so there are multiple steady state possibilities are there, and how the stability or that multiple steady states, that we will discuss basically. So, here let us say we are here's these lines, you can see this D line, that is RT, heat removal lines, and this is ES type of curve, that is called heat generation lines. So, this is heat removal lines and this is heat generations curve, that two lines we are getting, and here's you can see the 0.7, 0.8 and 0.9, these are the called means steady state temperatures, means for this particular inlet temperature of the feeds, 3 different points we are getting 3 different steady state temperatures. Okay. So, let us say if the operating temperature is TS8, this is that TS8, this is unstable point or unstable steady state stable point is called. So, if we operate the reactions at TS8 at this particular temperature, okay, and if pulse increase in the reactor temperatures, means reactor temperature, since coolant circulation is there, if we decrease suddenly coolant circulations rates, then heat removal rate will decrease. Okay. So, then heat generations would be gradually increase, heat removal terms lines will follow like this. Okay. And heat generations lines will follow this, means if sudden increase in the temperatures, a pulse increase in the reactor temperature is occurs when the reactions is means conducting at this particular point at this particular steady state temperature, and sudden or pulse increase in the reactor temperature, then what would happen. So, then heat generation, means heat generation terms would be more than higher than heat removals, means this part at this particular points heat generation is more than heat removal. So, if we reach particular point 9, so then this means from here heat removal generation is more than heat removals, and then gradually it would reach to the point 9s, until and unless we are reaching point 9 we will not get any steady state temperature. So, from 8 sudden jump or pulse increase in the temperatures, then heat generation should be more, and then it shift to the 0.9 that is the that steady state temperatures will reach, and the reactors will operate at this temperature. Here heat removal and heat generation both are same, okay, at this particular point. So, a sudden increase in the temperatures once the reactor is operating at steady state. So, then another new steady state temperature will reach. Okay. So, if we had a pulse decrease in the temperature at 0.8 pulse increase in the temperature we have considered, and now a pulse decrease in the temperature at 0.8. So, 0.8 at that particular steady state we are operating the reactor. If slight decrease in the or pulse decrease in the temperature is there, means due to the some error or something some way. So, then the lines will shift like this, heat generation lines would be this, and here you can see this is the heat removal line. So, here's line 3 means the heat removal is more than heat generations. So, then here's heat removal is more than heat generations. So, then the temperature will continue to decrease this way, the lines will follow and reach to the 0.7. So, lower steady state temperature to reach, okay, from 8 to shift and reach to here. So, if we pulse increase the temperatures, it would reach to the 0.9. If we decrease the pulse temperature, then it would reach from 8 to 0.7. So, that way means once a reactor we are operating in a steady state conditions, slight decrease or increase of the temperatures inside of the reactors. So, at different steady state we can observe. Okay. So, therefore, this point 8 is called unstable point. Okay. Unstable point is. So, if we operate a reactors at this particular steady state temperature, so if there is somehow increase or decrease of the temperature inside of the reactors, so then a new or different steady state we can get inside of the reactors. Okay. So, now if we let us say consider the reactions, and instead of point 8, since it is unstable point, so we will not choose to operate the reactor. So, we can choose point 9. If we operate the reactors at point 9 at that particular temperature, that we are choosing that steady state temperature and we are operating the reactor at that particular temperature. So, at this particular point once we are operating the reactors, so then if at that particular time slight increase in the reactor temperature at this particular temperature, so point 8 slight increase or decrease temperature, what would happen, that we have checked. Now, if we operate at the beginning and this particular steady state temperature, if we increase, I mean slight increase in the reactor temperatures, so then what would happen? So, then heat removal, this is the heat removal terms lines and this is the heat generation lines. So, here heat removal lines or it means slight increase in the temperatures, it would move like this. So, it would means heat removal slight increase in the temperature, there is no means harm for the reactor, since the reactor temperature will decrease and return to TS9, means if slight increase in the temperatures, there is no effect in the reactors, since reactor temperature will decrease and return to TS9. So, again it would slight increase and then again it decrease to the that particular steady state temperature. So, that is happen due to this, means heat removal is more than heat generations, therefore, it would affect or impact, there is no impact on that slight increase or decrease, slight increase in the temperature at this particular point. So, similarly, if we talk about point 7, at point 7 at this particular TS7, a slight increase in the temperature, particular TS temperature TS7 at that particular steady state temperature we are operating the reactor, and if there is slight increase in the temperature once we have started, this is case 1, this is case 2. Okay. So, case 2 means we have started the reactions at this particular steady state temperature and then slight increase in the temperature, if slight increase in the temperatures we will get this line. So, from here to it would move like this right directions. So, then it would reach here. So, here also we can see that this is the heat removal lines, this is the heat generation line. So, here also heat removals is more than heat generations, therefore, reactor temperature will drop to TS7. So, at these temperatures, these two temperatures we can stay stable steady state temperature and these are the unstable steady state temperatures. Okay. So, now we will discuss about one examples, means example means one's reactions, this is let us say this is the reaction sodium thiosulfate and hydrogen peroxide, if you take as a reactants and if we conduct the reactions, then this type of reactions may possibilities there inside of reactor. So, once these reactions we are conducting here. So, now we look into that, means different steady state temperatures that would be there. This is one example and here heat generations and heat removals with temperature we are plotting here. So, multiple steady state, what are the multiple steady state we observe, and once the temperature or any feed volumetric flow rates or space times if we decrease, so then what would happen inside of the reactors, means how the steady state temperature will change from one point to the another, that we will discuss. Okay. So, let us say the RT means heat removal lines is this for this particular reactions and heat generation line is this heat generation line this and heat removal line is this. First we will discuss this, and at this heat removal lines the space time, that is the volume by volumetric flow rate, space time, that is 12 seconds. So, that we are taken and these lines and this curve is there. So, both the lines are crossing rate points. So, these are the steady state temperature we can see for this particular reaction. So, when space time is 12 seconds, okay, space time 12 seconds we have taken, means space time how we can fix, volume is the constant, volumetric flow rate we can change. So, then by changing volume by volumetric flow rate, so we can fix 12 seconds, that is the space time. Okay. So, at this particular time, this is the steady state temperature you can see, and this is the steady state temperature. So, 4 degree, 33 and 80 degree centigrade, these are the temperature, means steady state temperatures under that conditions we can see, okay, under these conditions. So, once we operate, means volumetric flow rate, this is the volumetric flow rate, it was a particular and for that particular space time was 12 seconds. If we increase the volumetric flow rate, so if we increase the denominator, then space time will decrease, since volume is the fixed. So, then let us say space time at a particular volumetric flow rate is 6.8 second. So, means then at that particular space time, so heat removal lines will move this, means RT line was when 12 second was the space time, then heat removal lines was this, and when space time is 6.8, so then heat removal lines shift to this. Okay. So, then under these conditions, if we take this and this heat removal and heat generation line, both are intersecting at blue point. So, at this particular space time, so one steady state temperature we can see. Okay. So, this is close to 70. Okay. So, 70 degree centigrade. So, when space time dropped below 7 second, means 6.8 second. So, then the reactions steady state temperature drops 72 degree 70 degree centigrade. Initially it was 80 degree and then 33 and 4, these are the steady state temperature was there. So, now it is dropped to 70 degree centigrade. So, the flow rate, means here we have changes the flow rates, feed inlet flow rate, volumetric flow rate. The flow rate at which these drops occur is called blowout velocity, means at a particular velocity where this drops occurs is called blowout velocity. Okay. So, today what we have discussed, just I am summarizing this, means what we have discussed. So, we have started with means how to develop ignition extinction curves for a particular reactions when we operate in a reactors and their heat removal and heat generations is there, means coolant circulation is there, through that we can take out the heat from the reactor system. So, means energy balance equations, from the energy balance equations we have developed this RT and GT curve, and from there we can get the steady state temperatures at a particular feed inlet temperature. So, once we change the feed inlet temperature from one low temperature to gradually high, so then this heat removal lines will shift from this to this. Okay. Like that, if we take different feed inlet temperature, then these lines will move like this way. Okay. So, means if we started with a low feed inlet temperature, so then we will get this. If we gradually go high feed inlet temperature, we will get this heat removal lines. Okay. So, depending upon that, so many steady states we can get to operate the reactors, and that we have summarized. So, if you take this inlet temperatures, this reactor steady state temperature will get like that. Different feed inlet temperature, different steady state temperature we can get. So, that we have discussed. Now, we have plotted this to get ignition and extinction points for a particular operations, means whether increasing the temperature or decreasing the feed inlet temperature. By that way ignition extinction curves we can get, and we can get also the unstable state or unstable steady state we can get. Okay. And from the stability, means if sudden increase or decrease of the reactor temperature. So, then from the inside of the reactors when it is operating, so if heat removal is more than heat generations, then there is no problems inside of the reactors, means for that operations. So, that steady state we are means operating. So, at that particular steady state the reactors will operate. So, if heat generations is more than heat removals, then problems will appear, then another or new steady states will reach and their reactors will operate. So, means once heat generations is more than heat removals, so then what would impact on that, that we will discuss in our next class. Okay. and one examples we have taken, and there's what are the different steady state temperature are theirs, and if we change the volumetric flow rate of the reactants or feed. So, that way also we can change the heat removal lines and also the reactor steady state temperatures. Okay. So, thank you. So, today is up to this.